Classic Cosmic Conundrums 2. Hello and welcome to my channel. Let's say you go back in time, to a time when your grandfather was young. For some reason, you decide to make him disappear. This means that he will never meet your grandmother, your parents will never be born, and you yourself will never exist. The question arises, if you don't exist, how did you get back to the past? We often talk about the question of whether the universe is meaningful only because we are observers. We may be both observers of the universe and part of it. Whether or not this observation itself changes the nature of the universe may always remain a difficult puzzle. Assuming that the universe is infinite in size and time, it stands to reason that the arrangement of molecules, particles, and other tiny substances in the universe would at some point experience extreme fluctuations. Fluctuations that would most likely result in the formation of some kind of transient and anomalous, seemingly ordered structure. This structure may not be an object, but a conscious brain, even with a short memory and self-awareness. If you have a very thin rope, you can clearly perceive its length, but if the rope is curled or twisted at some microscopic scale, its cross-section becomes invisible. Such curling dimensions may not be directly perceivable by us, but they do exist and affect the physical world around us. Our attempts to understand the universe as it was created not only challenge our understanding of the laws of physics, but also force us to confront some very fundamental questions. What is nothing? If there is nothing, how can there be something? Can the universe be created from nothing? Today, I'm going to take you on a journey through 8 classic questions about the universe. 11. Observer bias. We often talk about the question of whether the universe has meaning only because we are observers. In fact, this question touches on some of the most complex intersections of philosophy and physics regarding how we understand the real world, the composition of the universe, and whether or not human existence is part of the fabric of the universe. First, let's briefly define the concept of observer bias. In everyday life, we might think of bias as some kind of inaccuracy or injustice, but in this context it refers to the fact that our understanding of the world is often influenced by the way we observe it. This influence is not just physical, but also cognitive and philosophical. In other words, the universe we see and perceive may, to some extent, be the result of where we are and who we are. As a simple example, you may have heard the argument that if a tree falls in the forest and no one hears it, did it make a sound or not? At first glance, this question may seem like a philosophical dilemma, but in fact it reflects how we confirm the existence of reality through observation. When a tree falls, it makes a sound, but the definition of sound is related to our perception. If no one is there to hear it, the sound is no longer sound, at least not in the sense that we normally define it. Similarly, the universe as we see it, or as we can understand it, may be meaningful only because we are observers. In other words, did the universe make sense before we existed? If no life, no intelligence existed, would the universe have any meaning? This brings us to the somewhat controversial philosophical proposition of the anthropic principle. The anthropic principle, in short, is the theory that many of the physical constants, conditions, and laws of the universe seem to be set up in such a way as to allow life to exist. In other words, we may be able to exist in, observe, and understand the universe precisely because the structure of the universe is tailor-made for us. If the physical laws of the universe were slightly different, life could not have been born in it. In a way, this principle raises a very interesting question. Does the universe exist for life, for observers, or not? Would the universe be meaningless without us observers, or would it still be the same universe that we can now describe in physics, but without the life to give it meaning? There is a very interesting point to be made here, borrowing a quote from the famous astrophysicist Stephen Hawking, who once said, "There are many possibilities for the universe, but the one we live in happens to be life-supporting." This is like a selective observation. We, as living beings, can only see those universes that support life. In short, we can't observe a universe that is not suitable for life. Our observation is inherently biased. Well, this is where we come to quantum mechanics, because there are some concepts in quantum mechanics that may give you a deeper understanding of the problem of observer bias. One of the most familiar phenomena in quantum physics is the so-called quantum observer effect. You may have heard of the double-slit experiment, which is one of the most powerful discoveries in quantum mechanics. In a nutshell, the experiment goes like this. If you let an electron or photon pass through a screen with two slits and don't observe it, it behaves like a wave, forming an interference pattern on the screen. But if you try to observe it by some means, it behaves as a particle and passes directly through one of the slits, forming two simple images and no longer an interference pattern of waves. This phenomenon is very confusing because it means that the electron seems to pass through both slits and exhibit fluctuations when it is not observed, and it does not exhibit particles until you look at it. And this begs the question, does our observation itself change the behavior of this matter? Do the physical laws of the universe only become apparent when we observe them? The quantum mechanic John von Neumann suggested that the collapse of a quantum state is dependent on the observer. In this model, the quantum world does not have a definite state before we observe it. It has multiple states, and it does not collapse into a definite state until we observe it. This intensifies the thought that the universe has meaning because of us. When we observe the universe, are we essentially creating the meaning of the universe? From a philosophical point of view, observer bias is not just a physical problem in quantum mechanics, but a profound proposition about how we understand the world. If the nature of the universe is somehow dependent on our observations, how can we understand reality? This question brings us back to the philosophical debate between idealism and materialism. Materialists usually believe that the world exists independently of our observations and that it has its own laws, structure, and way of being. We know it through perception, but that doesn't mean it depends on us, whereas materialists would argue that the existence of the world is intimately connected to the existence of our consciousness, and that the meaning of the universe itself is only revealed by the existence of human beings or conscious beings. A very interesting philosophical thought experiment is Plato's cave. In the ideal state, Plato describes, through the metaphor of a cave, how human beings are awakened from the reality of bondage into a real world. He argues that the images we perceive are merely projections of the real world, deviations from the truth. If we apply this analogy to observer bias, we might conclude that what we see in the universe may only be an image, and what is the truth? We may never know. Returning to the original question, does the universe make sense only because we are observers? From the point of view of quantum physics, it seems so. Certain properties and states of the universe seem to become clear only at the moment of our observation. We are like a participant who, by observing and thinking, gives the universe some specific meaning. However, from the point of view of the anthropic principle, the structure of the universe may have been set up in such a way as to be suitable for the existence of life, and our existence may not be accidental, but rather the result of some kind of nature. We may just happen to be in a universe that allows us to observe and understand it. Ultimately, there may not be a single answer. We may be both observers of the universe and part of it. Whether or not this observation itself can change the nature of the universe may always remain a mystery. 12. Time travel paradoxes. One of the most classic time travel paradoxes is the grandfather paradox. The logic of this paradox goes something like this. Suppose you go back in time to a time when your grandfather was young. You decide to make him disappear for some reason, like a revenge plot in a sci-fi movie or a boring prankster mentality. This means that he will never meet your grandmother, your parents will never be born, and you yourself will never exist. The question arises, if you don't exist, how did you get back to the past? This creates a self-contradictory loop. By going back in time, you prevented your grandfather from leaving offspring, but if your grandfather had no offspring, you could not have been born, and you could not have gone back in time. This logical self-defeating situation makes the grandfather paradox one of the most perplexing problems in time travel. Some might say, well, I don't kill my grandfather, I just prevent him from meeting my grandmother. Wouldn't that avoid the paradox? But the problem is that the paradox holds true as long as your actions cause your existence to become impossible. Physicist Stephen Hawking has proposed the time preservation conjecture, which suggests that there may be some mechanism in nature that prevents time travelers from changing the past in order to avoid time paradoxes. It sounds like the universe itself is fixing the timeline to keep everything in line, like some kind of time police operating in the shadows. But the question is, does time really fix itself? Or is there no such thing as a single timeline? Another time travel paradox that can be a real pain in the ass is the information loop, also known as the causal loop paradox. The classic example of this paradox is this. Suppose you're an avid Shakespeare fan, and you go back in time and realize that Shakespeare never wrote Hamlet. You are horrified and decide to write the play yourself and give it to the young Shakespeare. Shakespeare thinks this play you've given him is great and publishes it, and has been a literary giant ever since. Now the question arises, who actually wrote Hamlet? Shakespeare got the play from you, and you learned Hamlet from the future Shakespeare. But this means that the work itself has no real creator. It exists as a closed causal loop, like a magic box, with neither a beginning nor an end. A similar example is the science fiction movie The Terminator. In The Terminator, the core technology of the Skynet AI system is based on a robotic chip that falls from the future into the past. The technology of the future is reverse-engineered from the past, but the technology of the past is actually a product of the future, so where exactly did this technology come from? The problem with this information closure paradox is that it breaks with traditional cause and effect relationships. The basic logic of causality is that thing A causes thing B, but in the closed-loop information paradox, thing B is also the cause of thing A. The result is that the event appears as if out of thin air, with no real origin. This loop makes one wonder if our understanding of time is too simplistic. We have long believed that time is linear, like a river flowing from the past to the future with no turning back. But if time travel is possible, this means that time does not flow in a single direction as we thought, but can be broken, reshaped, and even split. One possible explanation is the many worlds theory, also known as the parallel universe hypothesis. This theory suggests that whenever you go back in time and make a change, the universe does not collapse, but splits into two different parallel universes. In the original universe, you do not go back in time and everything develops according to the original history. In the new universe, you affect the past and change the timeline, but the change doesn't affect your original universe. Think of it this way, you can go back in time and do anything you want without creating the grandfather paradox, because you're just creating a new parallel universe, not changing your original world. This theory sounds a bit implausible, but there is some evidence in quantum physics to support the many worlds interpretation, such as quantum superposition states and double-slit experiments. So, is time travel really possible in reality? According to Einstein's theory of relativity, time is not fixed, but relative. If you move at close to the speed of light, time slows down, which means you can travel into the future. For example, astronaut Scott Kelly spent a year on the International Space Station and returned to Earth milliseconds younger than his twin brother, Mark Kelly, a tiny example of the reality of time travel. But to actually go back in time would require a breakthrough in the deeper laws of physics. We know that wormholes are theoretically possible shortcuts through space and time, but how to stabilize them remains a mystery. Some physicists believe that closed time-like curves may provide pathways for time travel, but there is no conclusive evidence that they actually exist. The paradox of time travel makes us think, what is the nature of time? Is it one-dimensional? Multidimensional? Can it be altered? Perhaps we can never truly go back in time, but can only create a new future. Or maybe the universe has its own corrective mechanisms to make everything work the way it's supposed to. Whatever the answer, time travel remains a fascinating mystery, and it's these mysteries that allow our minds to jump into the wider universe. Maybe someday in the future we'll actually find the answer. 13. Boltzmann brain. The Boltzmann brain takes its name from the 19th century Austrian physicist Ludwig Boltzmann, one of the founders of thermodynamics and statistical mechanics. Boltzmann came up with this seemingly simple but highly far-reaching idea that in a large enough, infinite universe, entropy, i.e., the degree of disorder, would eventually lead to the disintegration of everything and increased randomness. A central idea of entropy theory is that all events in the universe have some sort of probability distribution, and that in a large enough system, chance and extreme events are inevitable. From this theory, scientists and philosophers then ask a perplexing question. Assuming that the universe is infinite in size and infinite in time, it stands to reason that the arrangement of molecules, particles, and other tiny substances in the universe would at some point experience extreme fluctuations that would most likely result in the formation of some sort of transient and anomalous, seemingly ordered structure. This structure may not be an object, but a conscious brain, even with a short memory and self-awareness. The Boltzmann brain was envisioned under such extreme conditions that consciousness could be a random thermodynamic event. That is to say, a brain could simply be a random arrangement of countless molecules in a corner of the universe, appearing instantaneously in time and space beyond our observation, and possessing a transient consciousness. It has no past or future, no actual life, but is simply a transient being with no past or future. It has no past or future, no actual life, just a brief, accidental, and meaningless moment of consciousness. The Boltzmann brain was not proposed as a solid scientific conclusion, but rather as a way to explore some deeper questions in cosmology and philosophy. The most intuitive impact is that it challenges our basic perceptions of reality and consciousness. Have you ever thought that you might not really exist? Or that all your memories, experiences, and self-perceptions might just be an accidental, meaningless existence? Maybe you don't live in a real universe, but in a contingent consciousness made up of thermodynamic fluctuations. Philosophically speaking, the proposal of the Boltzmann brain makes us question, is reality necessarily what we perceive it to be? Is there some unanswerable mystery hidden behind reality? Can we trust our senses and memories? Some philosophers have even suggested that if our existence is truly a thermodynamic fluctuation created by chance, what is the point of our existence? Suppose, for example, that you live in a completely real world full of memories, but the hypothesis of Boltzmann's brain reminds you that perhaps all the memories you experience, all the events you experience, are just a fleeting flash in your mind, whose authenticity and continuity are questionable. Maybe you don't really have a past or a history, you are just an instantaneous burst of consciousness. This mode of thinking is somewhat similar to the famous brain in a vat paradox, brain in a vat, which is a classic skepticism theory that human consciousness may just be a virtual consciousness generated by some kind of highly intelligent computer program, and that the outside world does not really exist, and the world we experience is just a virtual simulation. So why does this seemingly absurd hypothesis provoke such profound philosophical reflection? On the one hand, it reflects our inquiries about the nature of reality, and on the other hand, it has a subtle connection with certain theories of modern physics, especially the multiverse theory. Multiverse theory is a theory that proposes that there is not just one universe, but an infinite number of universes. These universes may have different physical laws, different initial conditions, and even different histories. It is some of the ideas in this multiverse theory that are behind Boltzmann's brain hypothesis. If we assume that the universes are infinite and that each one may have a different history, then according to the theory of probability, a fragment of one of the countless universes may, at some point in time, emerge as a completely random, ephemeral, sentient being which does not originate from any particular form of life, but rather is due to a completely random combination of particles, molecules, and other matter. From this perspective, a Boltzmann brain is not impossible. As long as the universe is big enough and time is long enough, it is possible to create a moment of consciousness by chance random fluctuations. Even in the framework of quantum mechanics, we will find that the disorder of quantum fluctuations seems to provide space for such accidental generation of consciousness. In some extreme cases, the instantaneous generation of consciousness is as natural as any other event that happens by chance in the quantum world. So how do scientists see this from a physics perspective? The existence of a Boltzmann brain is not completely irrational. Its assumptions are based on the second law of thermodynamics and probability theory. Let's look at why this is possible from a thermodynamic perspective. The second law of thermodynamics tells us that the entropy disorder of any closed system always tends to increase, i.e., the disorder of everything in the universe is increasing. However, this disorder does not mean complete chaos. It means that the arrangement of the parts of the system is getting closer and closer to a limit state. In an infinite universe, the increase in entropy brings about a great deal of randomness, and this randomness is likely to lead to the emergence of contingent phenomena, even including the emergence of consciousness. As an example, suppose the universe has endless time and space. In such a huge probability space, it is theoretically possible that our consciousness could randomly take shape at some point, like the shuffling of poker cards and the chance appearance of a very special hand. Although this is extremely rare, it is not impossible for it to happen. Scientists such as Richard Feynman have discussed similar probability issues, suggesting that although the probability of some quantum events occurring is extremely small, once the system is large enough and for a long enough period of time, the occurrence of chance events is almost inevitable. This is similar to the logic of Boltzmann's brain. The infinity of the universe and the infinity of time mean that no possibility can be ruled out, including the chance generation of a conscious being. The greatest challenge of the Boltzmann brain question is not just a scientific hypothesis, but a profound reflection on how we perceive reality. If there is a completely random consciousness that doesn't even have a real memory or history, are all of our experiences just the result of some kind of random fluctuation? How do we know we are not part of Boltzmann's brain? This reflection challenges our basic assumptions about existence, consciousness, and time. 14. Hyperdimensional life. The physical world of our everyday life is based on 3 dimensions of space plus 1 dimension of time, what we often refer to as 4-dimensional spacetime. Within this 4-dimensional spacetime framework, almost everything that exists and changes in our world is described based on these 4 dimensions. For example, we see objects with length, width, and height. This is 3-dimensional space, and an object's position in this 3-dimensional space changes with the passage of time. However, if you have had a little exposure to physics, especially relativity and quantum mechanics, you should know that this 4-dimensional spacetime framework is not absolute either. Einstein's theory of relativity gives us the idea that time and space are not static, and that they can interact with each other, depending on the state of motion of the observer. In the case of gravity, Einstein explained through general relativity that the mass of a celestial body curves spacetime, and that this curvature actually determines the gravitational phenomena we observe. This idea overturned the conventional understanding of Newton's time, but the situation becomes even more complicated when we talk about hyperdimensions. By hyperdimensions, we usually mean dimensions beyond what we can perceive in our daily lives. Much of the concept of hyperdimensionality comes from mathematics and physics, especially string theory and the multidimensional universe model. String theory is currently one of the most promising theories in physics, aiming to explain all the forces of nature, including gravitational, electromagnetic, weak, and strong forces, by unifying the behavior of all elementary particles. In string theory, particles are no longer point-like, but consist of extremely small, one-dimensional strings whose vibrational patterns determine different particle properties. What is even more exciting is that string theory is not limited to the familiar 4 dimensions of spacetime, but proposes a more complex model. Our universe may have as many as 10 or 11 dimensions. The dimensions here are not the ones we see or perceive every day, but are very tiny, curled up on very small scales. For example, if you have a very thin piece of string, you can clearly perceive its length, but if the string is curled or twisted at some microscopic scale, its cross-section becomes invisible. Such curled dimensions may not be directly perceptible to us, but they do exist and affect the physical world around us. String theory was developed not just to account for dimensions beyond our understanding of space, but to try to answer profound physical questions, such as how gravity fits into quantum mechanics, or why elementary particles have different masses and charges. So it is in this context that the idea of hyperdimensional life was born. Suppose there existed some form of life that lived in more spatial dimensions than we do, and that this multidimensional existence might be completely different from what we understand as life forms. How do we imagine these beings? Or perhaps there is no need to imagine them at all, as their existence is not limited by our perceptions at all. Suppose there is an extra-dimensional being whose existence is not limited to the 4 dimensions of space and time that we can perceive. In this case, our 3-dimensional space may be as limited for them as 2-dimensional space is for us. Perhaps their state of life does not require our common material form, but exists in a higher dimension of space. In other words, the form of these beings may be completely different from any creature we know, and their existence may not even be directly perceived by our senses. To understand this better, imagine that we live in a 2-dimensional world. If we could somehow observe a 3-dimensional object, such as a cube, we would realize that the 3-dimensional structure of this cube is very foreign to us. What we see is only a projection, or a 2-dimensional image of it. In this 2-dimensional world, the existence of any 3-dimensional object cannot be fully understood, and its thickness and volume cannot be perceived. In the same way, hyperdimensional beings may exist in dimensions beyond our reach, and the way they exist, the way they move, and even how they interact with the matter around them may be beyond our current understanding. From a scientific point of view, the form of extra-dimensional life may be the most challenging part. Assuming we are able to sense such beings, their forms and behaviors may be completely different from those of the species we know. It is even possible that some extra-dimensional beings may not have any of our common biological features, such as bodies or tissues. They may be complex energy structures of some kind, or mathematical objects that depend on multiple dimensions for their existence. For example, imagine a life form that lives in a higher dimensional space, where their shape could be a complex structure beyond our 3-dimensional understanding. If we were able to interact with them in some way, our senses might only be able to pick up a projection of one of their dimensions, just as we see a 3-dimensional projection of a 4-dimensional object. It is particularly interesting to note that the existence of extra-dimensional beings may revolutionize our understanding of language and communication. Language is the tool we humans use to communicate, but can we imagine that the language of hyperdimensional beings is not based on physical reality as we can understand it at all? There is a deeper issue at stake here. If these beings exist in a different dimension, the way they communicate may not be expressed through our existing language and symbol systems. They may communicate in a way that transcends space and time, exchanging thoughts and feelings through some form of information flow. Perhaps they don't rely on sound, light waves, or chemicals to convey information at all, but communicate directly through higher dimensional emotional resonance, or thought fluctuations. As you can imagine, in our 3-dimensional world, we use sound to convey information, but if you jump to a higher dimension, the way information is conveyed may change radically. Perhaps hyperdimensional beings could touch our brains in a way that would communicate their intentions directly to us without having to go through any physical medium. This idea is a bit fanciful, but from a theoretical physics point of view, it is not entirely impossible. The phenomenon of quantum entanglement in quantum mechanics can to some extent be regarded as a manifestation of instantaneous transmission of information over long distances. In quantum entanglement, the states of 2 particles are related to each other, and even no matter how far apart they are, a change in the state of one particle can immediately affect the other. Although we do not yet fully understand this phenomenon, it at least provides a clue. Perhaps the way hyperdimensional life communicates is somehow related to the non-local nature of this quantum entanglement. In exploring hyperdimensional life, we are not only discussing physics, but also reflecting on the philosophical level. The definition of life has always been controversial. Scientists usually define life as a series of specific biological processes, such as metabolism, reproduction, and genetic information transfer. However, as we explore the universe more and more, the definition of life appears to be broader and broader. Some scientists believe that life need not be limited to its chemical basis on Earth. For example, renowned physicist Mitchell Feldman has suggested that life could exist in other forms of material structures in the universe even if those structures don't fit our current biological definitions. In this view, hyperdimensional life could also be seen as some special form of life in the universe, except that they do not depend on the laws of physics that we are used to. 15. Infinite recursion in the universe. Things get complicated and fascinating when we discuss whether the universe is a fractal structure. Let's review the concept of fractal and see how it helps us understand the question. A fractal is a geometric structure that exhibits similar patterns at different scales, whether you zoom in or out. A common example of a fractal is the Mandelbrot set. Its mathematical properties can be summarized as self-similarity, where no matter how much you zoom in on a part of the Mandelbrot set, you will find new details and patterns that are similar to the pattern of the whole set, as if it were an infinite recursive process. And in nature, fractals are everywhere. The shapes of tree branches, clouds, snowflakes, and coastlines, for example, look fractal and have the property of being self-similar at different scales. These natural phenomena give us the intuition that if the universe is a fractal structure, it may have a similar structure at any scale, as if it were an infinite process with no end. What would our universe look like if it were fractal? We know that the universe has a wide variety of structures, from tiny atoms and particles to huge galaxies, clusters of galaxies, and even superclusters of galaxies. Through modern astronomical observations, we have been able to observe macroscopic structures in the universe, such as the filamentary structures between galaxies, which show a very regular distribution pattern. It stands to reason that if the universe is fractal, then these structures should be similarly arranged on different scales. Whether you're looking at tiny particles or galaxies hundreds of millions of light-years across, some of the features of these structures should be similar. For example, imagine that you are standing on Earth and see a grand starry sky. If the structure of the universe were fractal, you might notice that the structure of the universe shows a similar distribution at different levels, i.e., from galaxies to clusters of galaxies, superclusters of galaxies, and onto larger cosmic scales, each of which is similarly organized, as if a similar template exists at all these levels. And this pattern seems to have no boundaries or endpoints. The deeper you look, the more you discover new structures, as if opening up an ever-expanding labyrinth. This also raises an interesting question. If the universe is really fractal, and each level has similarities, does this mean that the universe is infinite? Because by the very definition of a fractal, there doesn't seem to be any clear boundary or endpoint. Whether you zoom in or out, certain patterns in the universe repeat themselves over and over again. Scientifically, this relates to the concept of recursion, specifically the idea of infinite recursion. In mathematics and philosophy, recursion is the process of repeating itself, or applying the same rules over and over again until it reaches a deeper level of structure. If the universe is fractal, then no matter what scale you start looking at, you will see the same patterns present themselves recursively over and over again. For example, in the framework of our current physics, the universe started with the Big Bang and gradually expanded to form the structure of the universe we see today. If the universe were fractal, this beginning would be blurred. It is possible that the universe is not a linear process that started from a point in the explosion and has evolved to the present, but rather a recursive cycle where each stage is similar to the one before it, as if it were some kind of never-ending repetition. From this point of view, the infinity of the universe no longer refers to some kind of edge that we can't observe at the moment, but to the fact that the structure of the universe is always repeating itself at different scales, and there is no real end. There is no real end. No matter how much we try to explore the boundaries of the universe, we can't seem to find an end point. When we talk about the fractal universe, we have actually touched the boundary of physics. Current cosmological theories, especially models of the universe based on the Big Bang theory, assume that the universe had a definite beginning, the Big Bang, about 13.8 billion years ago. But if the universe is fractal, or if its structure exhibits infinite recurrence, then our current understanding of the origin of the universe becomes less clear. In addition, quantum physics offers some concepts that are similar to those of the fractal universe. The phenomena of quantum entanglement and non-locality in quantum mechanics somehow also show us that there is a kind of self-similarity in the universe beyond our intuition. In the microscopic world, the behaviors of particles show an elusive interconnection, and it seems that some laws of the universe are similar at some levels, and there may be an intrinsic unity between different physical processes. At the same time, string theory also attempts to deconstruct the universe from higher dimensions, suggesting that our universe may not be three-dimensional, but rather composed of more dimensions, and that these dimensions may also exhibit fractal properties. String theory researchers believe that the nature of the universe is not just a three-dimensional material world, but also includes a deeper structure that may be fractal in nature. From a philosophical point of view, the infinite nature of the universe is also often the subject of discursive thought. Plato once put forward the concept of ideal forms, believing that the real world is the image of the ideal world, behind which there is some kind of eternal, unchanging structure. The fractal universe, to a certain extent, can also be regarded as an embodiment of the ideal forms. Each of its scales follows some kind of eternal law, as if each level can reflect the prototype of the whole universe. Karl Popper's theory of falsifiability suggests that any scientific theory must be able to be disproved, otherwise it is not scientific. The discussion of the fractal universe faces a similar challenge. If the universe is infinitely recursive, how can we experimentally and observationally verify the structure of the universe? Can it be a falsifiable scientific hypothesis? Or can the question itself only be regarded as a philosophical debate? Back to the core of the question, are we living in a universe with a fractal structure? From the available observations, the structure of the universe does show a certain degree of self-similarity. For example, the distribution of large-scale structures such as galaxies and clusters of galaxies in the universe seems to show some similarity at different scales. However, whether this means that the structure of the universe is fractal remains an open question. Scientists are still exploring this puzzle, and we may get more clues in the future as observational techniques develop. But no matter what the answer is, this thinking about whether the universe is infinitely recursive has fueled our curiosity about the universe and our desire to explore the unknown. Perhaps in the future, we will find that the universe is not just a huge physical body, it is an endless philosophical puzzle. 16. Eternal return. The passage of time is so real and unavoidable for all of us, however, with the development of science and philosophy regarding the nature of time and its structure, we gradually begin to realize that it may not be as linear as we thought, always moving forward. Eternal return, a seemingly ancient and perplexing concept, has once again become a hot topic of debate in philosophy and physics in recent years. Could the universe be in some sort of constant loop or not? If time is truly infinite, then any event could repeat itself to some degree. So is all of this in our lives part of some sort of ultimate cycle? If eternal return is an esoteric philosophical question, it is best represented by the German philosopher Friedrich Nietzsche. In his work, Thus Spoke Zarathustra, Nietzsche put forward the concept of eternal return. According to him, assuming that the universe is infinite in time, every event and every moment, no matter how insignificant, will be repeated in the same way at some point in time. In other words, every time we experience will eventually come again, and we will experience it again and again. This proposition not only deals with the structure of the universe, but goes deeper into how we view life, choices, and the meaning of existence. Nietzsche did not come up with this proposition as mere philosophical reasoning. He wanted to use it as a way to bring people face to face with the absurdity and pain of life. He challenged our attitude towards life through this concept. Could you live comfortably if you knew that every decision you made, every pain you suffered, would be repeated in the same way over and over again? This idea of eternal return is the ultimate questioning of human choices in a finite life. In Nietzsche's philosophy, eternal return is a shocking thought experiment, which makes people examine every moment of their lives and consider whether they can still hold on to their choices and beliefs in an endless repetition. It's not just about the cycles of the universe, it's about how to give meaning to life. While the eternal return proposed by philosophers is full of far-reaching discussions, can physics provide some clues? If time is infinite, could the universe actually go through some form of cycle? The answer does not seem so simple. From a thermodynamic perspective, the evolution of time and energy in the universe is not an infinite loop. In classical thermodynamics, the second law states that the entropy, i.e., the degree of disorder, of all closed systems increases with time, eventually reaching a state of maximum entropy without any change, the so-called heat death. In other words, the energy in the universe will gradually be evenly distributed, all physical processes will stop, and time and space will become meaningless. Thus, the concept of heat death seems to be in direct conflict with eternal return. How can we talk about cycles if everything tends to be uniform and static? However, physicists have also suggested some possibilities, trying to incorporate the theories of modern cosmology to consider whether the universe might undergo some form of cycling. For example, concepts such as quantum gravity, string theory, and the multiverse theory give more complex, but also highly imaginative answers. In some models of cosmology, the Big Bang is not the only birth event of the universe. Theoretically, the expansion and contraction of the universe can occur repeatedly, and each expansion can be a new Big Bang, followed by a new Big Crunch. This creates a cyclical process. The universe undergoes expansion, expands to its limit, and then gradually contracts, and then may explode again and start over. This theory is known as the oscillatory universe theory. The oscillating universe theory is inspired by the theory of general relativity, which theorizes that the expansion and contraction of the universe may be due to gravitational forces that eventually allow the universe to stop expanding and start contracting at some point. Scientists propose that as the universe contracts and re-explodes, the laws of physics, the structure of time, and even space may be rearranged, and that the universe in each cycle can be viewed as a completely new world with different conditions and events. However, this theory has not yet been fully tested and faces many challenges, especially since today's cosmological observations show that the expansion of the universe is not slowing down, but rather accelerating. In addition, with the discovery of dark energy, scientists are beginning to realize that the accelerating expansion of the universe may never stop, and that the universe will continue to expand forever, eventually entering an eternal state of cold silence. Thus, while this theory is intriguing, current scientific data does not seem to support the idea that the universe undergoes periodic contractions and expansions. If the Big Bang and cosmic contraction theories on a macroscopic scale do not support an eternal return, does quantum mechanics offer a new perspective? In the microscopic realm, the uncertainty principle of quantum mechanics and the properties of the wave function give us another idea of the infinite cycles of the universe. Quantum mechanics reveals a world of uncertainty and fluctuation, where particles may exist in more than one state at a time, a phenomenon known as superposition of states. Some theoretical physicists have suggested that quantum gravity and string theory may reveal deeper laws behind the universe, and may even demonstrate the nature of eternal regression in some parts of the universe. More specifically, the multiverse theory of quantum theory suggests that the universe we see may be just one of countless parallel universes. Each universe follows a different physical law and origin story, and there may be some form of interaction or connection between these universes, possibly in the form of a cyclic or regressive pattern. Although these theories are still in the research stage and even have many unresolved issues, they give us a new possibility. The universe is not just a linear story, but it may be infinitely cyclic or exist in many forms in ways we cannot foresee. 17. The creation of the universe out of nothing. As we try to understand it, not only challenges our understanding of the laws of physics, but also brings us face to face with some very fundamental questions. What is nothing? If there is nothing, how can there be something? Can the universe come into being from nothing? This question goes back to the first moments of cosmology, and naturally we are talking about the origin of the Big Bang. But a deeper exploration touches the edge of the intersection of philosophy and physics, especially the concept of something out of nothing, which is a challenge not only for physics, but also for philosophy. Whether you are a skeptic or a believer in science, you may ask the question, how could the universe come from nothing? Where could there be a universe if there was no time, space, or matter? However, with the advanced development of quantum mechanics and quantum field theory, scientists have come up with a seemingly counterintuitive idea. The universe might actually be born from nothing, and this nothing is not our traditional nothing. It 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 is not our traditional nothing. And this nothing is not the absolute emptiness that we traditionally understand. In the framework of quantum field theory, our universe is not an eternally existing nothing, but a void filled with quantum fields, which we cannot see or touch, but which is not completely empty. According to quantum field theory, every particle, every substance in the universe, even light, is an excitation of a quantum field. When we say that the universe was born out of nothing, we actually mean that the universe could have been born out of this energy-filled void. The void is not empty, but full of quantum fluctuations, which are natural phenomena in quantum mechanics. We can imagine a quiet lake. It seems to be calm, but occasionally there are small fluctuations. These fluctuations can be suddenly appeared and disappeared at any moment. Quantum fluctuations are similar on a microscopic scale. In a vacuum, energy is constantly bouncing, and even pairs of particles and antiparticles are constantly appearing and annihilating in a short period of time. You might think, isn't that just nothingness in the void? In fact, it is these tiny, accidental ups and downs that allow matter and energy to be born. The emergence of quantum fluctuations provides a state of nothing from which the universe can be energized. Let's understand quantum flux more intuitively. Suppose we look at the microscopic state of the universe. According to quantum field theory, the vacuum is not completely static, but full of tiny energy fluctuations. Such a state seems to imply that the universe could explode out of this potential void. The Big Bang, the event we commonly understand as the birth of the universe, could have arisen by chance from such a quantum fluctuation. Physicists usually explain this with the example that if the void is filled with infinite energy, these fluctuations of energy may suddenly explode at a certain moment, forming the first particles in the universe. And this is the beginning of the birth of the universe. Similarly, through some kind of invisible collision, the original empty void was stimulated by some kind of energy and eventually evolved into the universe we see now. The fact that the rise and fall of the void is a direct consequence of quantum mechanics is confirmed by quantum electrodynamics. In the quantum electrodynamic model, the void is not a ubiquitous nothing, but a state full of tiny energy fluctuations and particle-antiparticle pairs that are constantly generated and annihilated. Although they are not persistent, the energy of these fluctuations is sufficient to form a surge and provide the initial impetus for the expansion and evolution of the universe. However, all this seems to be more than a matter of physics and brings up philosophical considerations as well. If the universe was born out of nothing, or if it originated without a founding cause in the traditional sense, this would be like an uncaused occurrence. This point touches on an ancient philosophical reflection, the first mover. The unmoved mover is a concept put forward by the ancient Greek philosopher Aristotle, who believed that all changes in the universe have a cause, and this cause itself is unaffected and does not need to be pushed, that is, the first mover. This idea has influenced the development of Western philosophy and theology, and many philosophers have argued that the universe must have a primordial impetus, that is both the source of its beginning and the reason for its continued existence. From this perspective, the origin of the universe seems to require an external, transcendent force to explain it, a first mover. This is also the theory in many religious and philosophical systems about God or the absolute being, some kind of eternal, unchanging being that causes everything to happen and change. But if we look at it from the perspective of quantum field theory, does this first mover need to exist? According to the quantum field theory interpretation, the universe may no longer need an external mover in the traditional sense, but rather evolve naturally from a void full of potential. The quantum fluctuations in the void may be capable of triggering the birth of the universe itself, or even of spontaneous existence without an external mover. This contrasts with Aristotle's notion of a first mover and suggests a new perspective on the self-generation of the universe. In other words, the universe could be self-initiated, not requiring an external driving force, but being born from nothing through some internal mechanism. The perspective of quantum mechanics allows us to go beyond the traditional philosophical framework of thinking about the origin of the universe, which reveals a causal chain that may be causeless. The universe itself may be a result of the rise and fall of quantum mechanics, or the birth of the universe itself may not have been triggered by an external cause. Or the birth of the universe itself may not have been triggered by an external cause, but by some tiny quantum fluctuations. But then the question arises, if there is no first push in the traditional sense, how did the universe arise spontaneously from the void? Quantum fluctuations do explain how the universe could have emerged from nothing, but does this explanation go far enough to address the philosopher's deeper questions about existence? For example, why is there a void? Does emptiness itself require some kind of transcendent being to explain it? These questions cannot be solved by physics alone. They also touch on philosophical considerations. Perhaps the origin of the universe, like its endless vastness, is an abyss that we can never fully touch. 18. The simulation hypothesis. The core of the simulation hypothesis can be boiled down to a simple question. If human civilization advances enough, is it possible to simulate a virtual universe through computers that is exactly like the real world? This may sound crazy, but it was actually proposed by none other than philosopher Nick Bostrom, who in 2003 presented a paper entitled, "Are We Living in a Computer Simulation?" in which he made the startling argument that if future supercivilizations were powerful enough to perform large-scale computations, it would be possible to run a virtual world that would be almost identical to the real world. Virtual world that is almost identical to the real world. And every person, every object, even every tiny atom in this virtual world could be created by this supercivilization. Bostrom's reasoning logic is divided into three core assumptions. 1. The future civilization is advanced enough to carry out ultra-large-scale calculations to simulate every detail of the real world. 2. These supercivilizations are likely to conduct simulation experiments and may create countless virtual universes. The purpose of the simulations could be to study history, test hypotheses, or even for entertainment or other purposes that are difficult for us to understand. 3. We could be living in one of these simulated worlds. If a supercivilization can create a virtual world and repeat its experiments through an infinite number of simulations, then it is possible that we, as inhabitants of the simulation, are part of the experiments of some advanced civilization. From these three assumptions, Bostrom draws a fascinating conclusion. If future civilizations are powerful enough, they will conduct a large number of virtual simulations, and the number of these simulations will far exceed the number of real worlds. Thus, from a probabilistic point of view, the likelihood that we will live in a simulation may be far greater than the likelihood that we will live in the primitive physical world. If we do live in a simulation, how does the simulation work? Would it be a holographic virtual reality like the Matrix, or would our perceptual world be generated through more sophisticated computation? First, we need to think about the level of simulation. Assuming that a supercivilization is able to create a simulated world, their computers must be able to simulate all the details of human behavior from the most microscopic laws of physics to the macroscopic. That is, the simulation must not just make it look like we are here, but even how our brains perceive information and interact with our surroundings must be accurately modeled. Here is how the simulation is structured and how it operates. 1. Particle-level simulation. A very basic idea is that the simulation must start with the most fundamental laws of physics. Just as we live in a world of atoms and particles, if a supercivilization wants to replicate this world, it needs to simulate the behavior, interactions, and processes of change of each particle. This is like creating a super-complex program in which each line of code represents the state and movement of a particle. As long as the simulation of these particles is accurate, our brain and sensory system will be able to perceive the existence of reality. 2. Macro-behavioral simulation. In addition to accurate simulation at the particle level, the simulation also needs to simulate more macroscopic phenomena, such as weather, climate, the movement of the Earth, and even the mode of operation of society. These macroscopic behaviors need to be controlled by algorithms and rules, such as chaos theory can be used to simulate the complexity of weather systems. Every decision, every war, and even every joke in the simulated world may be generated by a computer based on established rules and algorithms. 3. Simulation of consciousness and cognition. This is a very important point in the simulation hypothesis. If we live in a computer simulation, how does our consciousness as a simulacrum exist? A supercivilization would need to simulate not only how we perceive the world, but also our complex mental activities such as thinking, emotions, and consciousness. In other words, not only our bodies and behaviors, but also our subjective experiences must be completely simulated. This brings us to the philosophical mind-body problem, which is how the physical state of our brain corresponds to the creation of consciousness. Of course, this all sounds very complicated, so how could a supercivilization do this? The answer may lie in the fact that their computing power and technology are beyond our current imagination. Assuming an unprecedented level of computing power in the future, even capable of handling huge amounts of data beyond our comprehension, simulating an entire universe would no longer be a challenge. Quantum computing could be the key to solving this problem, with quantum computers able to handle a large number of computing tasks simultaneously, breaking through the computational bottleneck of classical computers. So how can we prove that we are living in a simulation? This point is certainly the most challenging part of the simulation hypothesis. How do we prove that the world we live in is actually an elaborate computer program? This question has always been a very difficult one in the scientific and philosophical communities. We can look for evidence of simulation. 1. Computer flaws. One way to think about this is that we may be able to find some programming errors in reality or unnatural phenomena in the simulated world. One way to think about this is that we may be able to find program bugs in reality or unnatural phenomena in the simulated world that do not conform to the laws of nature as we understand them. For example, in a simulated environment, there may be things that appear to be miscalculations. For example, the laws of physics may not follow exactly what is expected, or some regular physical phenomena may not be explained. Like the black cat playback in The Matrix, if we see a certain pattern repeated in reality, it may mean that the world we live in has been simulated by a computer. 2. Observing particle-level resolution. Another way to look at this is that there may be a resolution limit to the simulation. Just as when we play a video game, objects in the game screen may look blurry at a distance, or in a computer simulation, the precision of particle motion may be limited. If we can find certain anomalies at the microscopic level, such as changes in quantum states that can't be explained by classical physics, or the structure of space and time showing some unusual patterns, it may prove that we don't live in a completely natural physical universe. 3. Energy limitations of simulated worlds. According to some physicists, the operation of simulated worlds may require the consumption of enormous computational resources. If these resources are limited, the simulation may not be able to fully model every detail of the entire universe, which may also be a clue to our discovery of the simulation. For example, the boundaries of certain astronomical phenomena may not be fully simulated due to the limitations of computational power, thus revealing traces of simulation. Returning to the original question, if we were living in a computer simulation created by a supercivilization, how would we perceive our existence? The simulation hypothesis forces us to rethink fundamental questions about reality, consciousness, and existence. It challenges our perceptions of the world and raises the intriguing but disturbing hypothesis that everything we live in may be nothing more than the program code of some supercomputer. Whether or not it can be proven that we live in a simulation requires more thought and exploration, and perhaps advances in science will give us new clues. Either way, the simulation hypothesis reminds us that the world as it really is may be far more complex, mysterious, and elusive than we think. Well, that's it for this installment. Kudos and comments welcome, and thanks for tuning in.